Hello everybody and welcome back. Today we're going to be talking about springs and how to solve problems when they're in parallel and in series. But before we begin, let's go ahead and talk about springs in general and the equation that governs their movement. So we have the force equals negative kx. This is Hooke's law. And essentially what this is it's saying it's the negative, this is the spring constant, and this is the displacement from its equilibrium. And so it's negative because it's a restorative force. So if you pull a spring away from its equilibrium point, no matter which direction, it's going to return or want to return back to its equilibrium point. So the force is going to be acting opposite to the direction that you pull it, no matter what. And so here we have two different situations. So we have it in series and then we have it in parallel. And so what we're going to say is that, okay, so for series, we're trying to find this total k value. And for that, it's 1 over k1, which is the first spring constant, plus 1 over k2, plus all the way over to the 1 to the k-nth. And then for its force, it's just going to be, that's the force total, it's going to be the sum of force 1 plus force 2, all the way up to the nth force. And this is for series. Now for parallel, it's a little bit different. But the forces is going to be the same, but the k value is going to be different. So kt equals k1 plus k2 plus all the way to the kn, and the total force is going to be equal to the sum of the forces. So that is the same as when it's in series, but this is for parallel. So as you can see, it's a little bit simpler for when they're in parallel, but when they're in series, you have to do the reciprocal. So it's, you have to involve fractions. But I think in order to better understand this, let's look at an example problem. So here we have a bunch of springs that are in both series and in parallel. We have them in parallel going up and down, and in series going this direction. And so what we have here is the equilibrium position is right here. So you can imagine the spring has been squished to that point, or it's usually in that point, it's been stretched all the way over here. 0.25 meters away from its equilibrium position. So in order to find this, what we need to do first is understand, okay, so let's work in parallel to do it first. So let's look at this column right here. So we can say that k total 1 equals k1 plus k2 plus k3. And that is going to be 2 plus 1 plus 3 Newton meters. So that is 6 Newton meters. And then for this column right here, we only have k4 plus k5, and that's 1 plus 2 Newton meters, so that's going to be 3 Newton meters. And then if you notice they're in series here, so what we have to do is take the reciprocal. So 1 over kt1 plus 1 over kt2 is going to equal the 1 over the actual k value. And so if we look at that, what we have is 1 over 6 Newton meters plus 1 over 3 Newton meters equals 1 over this k total. And so if we're looking at this, we have, all right, so 1 over 6 plus 1 over 3, which equals 0.5. So 0.5, 1 over newtons per meter, which is a little bit different, equals 1 over the total k value. So we need to multiply by kt on both sides and divide by 0.5. So we get kt equals 1 divided by 0.5 Newton meters. So the total k value equals 2 Newton meters. So this is our value for kt. And so what we can do now is plug it back into the equation for Hooke's law. So we can sort of divide off this little portion, and we can say that, all right, so we have the force of the spring equaling negative k total times the displacement, and so that equals negative 2 Newton meters times 0.25 meters. And notice that the units here, the meters in the denominator of the spring constant cancel out with the meters of the displacement from the equilibrium position. So what we're left with is negative 2 times a fourth, so negative 2 divided by 4, which equals negative 0.5 newtons. And it's in newtons, and so that is what we want for the force, or for any forces we want it to be in newtons. And so that is the total force generated by this spring here.